Hello everyone, welcome back to the channel. This is Dr. P Aerospace, and today we're going to be continuing our discussion on the conservation of mass and integral analysis, and specifically going over an example problem. And this example problem is going to take up the entire video because there's a lot of math, and I really like to go through kind of rewriting out the math so everyone sees the exact step-by-step, because when I was learning, I was very frustrated that every math step was not included, because if I made a mathematical mistake, it just took a lot more time to kind of understand where I made the error. So I'm going to be doing a lot of rewriting. So feel free to skip through uh, some of the video, but this is going to be quite long because we're going to be very meticulous about doing the math and understanding kind of how we get to our final answer. So without further ado, let's jump right into it. So liquid drains through a funnel of dimensions as given in the figure below. Velocity of the liquid leaving the funnel can be found at any instant. Part A, obtain an expression for time t required to drain the funnel. Express the result in terms of initial volume and initial volumetric flow rate. Part B, if the hole diameter is 5 millimeters, plot the time to drain the funnel as a function of y naught over the range from 0.1 meters to 1 meter with an angle range between 15 and 45 degrees. Okay, so at first glance, this doesn't look too crazy, but we have a volume that appears to be draining with time. So it's definitely going to add a layer of complexity that we have not done in the previous three example problems. So step one is to list out your assumptions. And again, I'm going to drive this home to everyone in the audience. If you are not listing out your assumptions as the first thing you do, you should be getting points off your exam or homework or whatever. It's so critical. Okay, so assumption number one, we have a liquid here. So we can immediately assume incompressible flow. Next, if we, say our control volume is this region right here, bounding our liquid and the surfaces of the funnel and the bottom orifice, that will be our control volume. And because we have a gravity-driven flow, right? Gravity is kind of driving the liquid to go out through the bottom. This upper surface is going to be changing with time. So y is a function of time here. So we definitely have a deformable control volume. First example problem where this comes up. Next, we have to make an approximation for the volume here. So, the volume of a funnel, it's it's not that it's hard, but it gets kind of nasty when you have to start doing integration and stuff. So to keep it simple, we can actually make an approximation that this funnel is basically like a cone. Like we can represent the volume as a cone. And this is especially more understandable if we look at part B, where we see the hole diameter is only 5 millimeters, but we see that the range of y naught that we have to plot over is zero point 0.1 to 1 meter. So kind of the ratio between the diameter and the height of the cone is very significant. So we can definitely approximate this as a conical volume, not a funnel volume. Okay, and then next, this isn't explicitly stated here, but we can make this assumption. Some textbooks will probably have an indication here like this, but the upper and lower surfaces of the funnel are open to atmosphere. ATM, that's a really bad atmosphere there. So P equals P atmosphere everywhere outside of the cone, including at the exit where the water's coming out. I'm going to assume it's water. It says liquid, but it looks like water. Okay, and then lastly, let's assume that the velocity profile is uniform at the exit. Okay, great. We have a very nice starting point of assumptions here. So now let's jump into conservation of mass as our starting point. Okay, and everyone's memory at this point, it's del over del t, integral over our control volume of rho dv plus integral over our control surfaces times rho v dot n dA equals 0. Okay, so let's just start crossing out a couple things based on our assumptions. So we have incompressible flow, so we can knock out density. We have a deformable control volume, so unfortunately we can't do anything with this unsteady term here. And the rest of our assumptions don't really have any impact immediately on this kind of baseline form of conservation of mass. So that's pretty much our starting point. Now, when I rewrite this, first I'll rewrite the volume term here. This will be del over del t, integral over our control volume. This will be dv. And now I'm going to start writing out our terms here. So we have two, I guess, main surfaces where we could technically mass crossing the boundaries. We have surface 1, which is the top surface, and surface 2, which is the bottom surface here. So you would have, and again, this is very redundant right now. Like, there's no reason that I need to be writing the integrals for this, but I'm just, again, driving home these concepts to everyone. So I wrote this out, but we're basically just going to cancel out control surface 1 because the velocity, I mean, there's no velocity crossing the control surface there. So that would be an entire cancellation right there. And because our outflow for control surface 2, or we have outflow for control surface 2, and it's in the same direction as our, unit normal vector here, we're going to have a positive value outside of our integral there. So let's rewrite all of our terms again. This will be plus, and then if we evaluate the dot product, it'll be a scalar. This will be v2, and it'll be multiplied by our area 2. Now, this was written as a kind of differential dA2, but we mentioned before that the velocity can be assumed to be uniform, and the problem already told us that the whole diameter, I mean, it's fixed area, it's not changing with time or anything. So dA2 can actually just be written as a um, like a kind of total area, just like that. And because of the uniform velocity, we don't even really have to integrate over anything because these two values are fixed. Okay, great. So we've started to make some simplifications. So two things I noticed that we have to start making progress on. We have the dv term and this v2. And you might be asking, like, why do we need v2? Like, v2 can just be v2, right? No. Unfortunately, v2, it has to be solved for using kind of some other relationships of fluid mechanics, which hopefully you've learned before getting into these kind of videos on integral analysis, but we'll go through that in a moment. Um, we have to find out what v2 is in terms of uh, y, like how is it changing with respect to y. So to do that, we're actually going to use Bernoulli's equation. And we're basically going to say that we're taking 2 points. Point 1 would be like right here at the very surface, and point 2 would be at the exit. And we'll just apply Bernoulli's equation. If you're confused on where this comes from, I don't have a video on this yet. Hopefully, I will in the future. But it's a very simple concept. It's basically an equation that can apply to incompressible flows, and it's very useful for like solving questions based on like water, like fluid flows, like liquid flows, and things like that. So this will be P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho g y2. And now we can start canceling stuff out of Bernoulli's equation. So because we're at atmospheric pressure all around this cone, P1 is equal to P2, and therefore P1 minus P2 when you move them onto either side would just cancel out. Next, if we assume that this bottom part of the cone is y equals 0, that would mean y2 is equal to 0, and this term cancels out. Then we have v1 squared here. As we already had stated above, velocity at point 1 is pretty much 0. Now, you might be thinking, well, you said the control surface is changing with respect to time. Like, why? How do we not consider that? Well, first off, it's draining very slowly, which you'll see when we plot our final results for part B, because our whole diameter is only 5 millimeters. So it's going to be very, very close to 0, but also the liquid itself is kind of stagnant here. This control surface is going down, but the liquid is pretty much stagnant. So V1 is 0. And then we have incompressible flow, so our densities will cancel. And then after that, we have gy1 equals 1 half v2 squared, which means v2 equals v2 times g times y, like that. And you might be asking, like, why didn't I put a subscript 1? Because the way the problem was kind of formulated, based on how it was presented to us, it was saying that y is basically this upper surface here. So we used a subscript 1 to kind of denote where we were applying Bernoulli's, but for this purpose, we're just going to keep it as a flat y variable. Okay, so we have one piece of our puzzle unlocked, so we can plug v2 in, which is now a function of y, which is also a function of time. And then, let's see here, we have our dv term, and this is where things get kind of unnecessarily mathy, and you'll see what I mean in a moment. So let's I'm going to try to separate this on this slide, and then we'll rewrite everything together afterwards. But so this will be this term here, dv. So we said in our assumptions that we can approximate the volume as a cone. So let's kind of start off there. V cone equals, just by definition, pi over 3 r squared times our height. In this case, we're going to use y as our height, which varies with time. Oops, there we go. But you'll see that our relationship has a differential volume. So how do we write a total volume in terms of differential volume? So this is kind of the first area where people get super tripped up. So we need to find what dv of cone is. We know it's going to be some integral because, I mean, that's quite literally what we're doing here. We're integrating over the control volume. So how do we rewrite this? Well, let's look at a cone here really quick, a very poorly drawn cone. I'm actually going to redraw that. I'm upset at how bad that cone was. that was awful. See, that might be better. That's much better. Okay. So what is a cone at its fundamental? Well, it's basically a bunch of disks with varying radii, I should say, radii stacked on top of each other, like this, right? All the way down to the very bottom, where your bounds would be from like, y equals 0 to y equals yf. And you would integrate over y. And that's basically all we're going to do here because the water level is changing with respect to y. It's not changing from the left to the right in the r direction. So we can assume that our differential is definitely going to be in the like a dy. We're not going to have a dr or anything like that. So we're going to basically use this kind of summation of a bunch of tiny circles between our different y bounds in this integral, which would be area of a circle, pi r squared, times dy. Pi r squared is the area of a circle, and we're going integrating over the y direction here. And that's all it is. And that would be from like 0 to yf, y final. Then the other thing we have to work on, though, is that this dv cone is in terms of radius. And part B is very clearly asking us in terms of theta and not radius. So we actually have to find out what radius is in terms of theta. So if this is r, and we have like our height of this like triangle here that I'm trying to draw. Let me just draw this in red so it's a little bit clearer for everyone. All right, this is theta, this is y, this is r. A little challenging to see, but I think it's coming through clear enough. This is just trigonometry, so all you have to do is see that tangent theta is equal to r over y. So therefore, r would be equal to y times tangent theta, just like that. I'm gonna quickly draw out some areas over here so we don't get confused. And then basically we substitute this r value into our dv relationship. This would be dv equals, try not to write on my face right here, I'm getting kind of close. Integral, this would be pi times y squared, tangent squared theta, dy. Perfect. So that's dv of the cone. That's what we're going to substitute in for this portion right here. So we have our two kind of unknowns that we needed to solve for to move forward with conservation of mass. Now let's rewrite this on the next page. So let's start off. Here's integral of our control volume, del over del t, dv plus integral. Let's go back again. What I'm actually going to do when I rewrite this, I'm going to move this v2 times a2 to the other side of the 0, so it'll be negative. That's all I'm going to do in this next step here when I'm rewriting it. So let me erase this. Just like that. And then let's substitute our values in. So we have to substitute a value for v2 and dv. This will be equal to d over dt integral. I'm going to hold off on the bounds for a second on this integral, and we'll come back to that. This would be pi times y squared tangent squared theta dy equals negative square root of 2gy times a2, just like that. And then one thing we have to do here is convert this partial derivative into a total derivative, because our kind of entire equation here only has two variables that are changing, the y and the t. If there were other variables, then we'd probably have to start getting into the partials, but that's definitely not relevant right now. And most of the time, in any class you're dealing with, you're pretty much never going to have to deal with a partial term. Most of the time, you'll end up dealing with the total derivative. From there, we'll just move this total derivative of time to the other side, and then we can rewrite this out. Again, lots of rewriting. And basically, I'm moving dt over here, and then we're integrating. So this would be negative root of 2gy a2 dt. So if you're in the audience and you're like, something's wrong with this math, you're absolutely correct, because we can't be integrating dt over here and dy over here when there's still a y right here. So we actually have to move and divide out a y to the 1/2 so we can bring it over to this integral over here. So when we do that, we end up with pi, this would be y to the 3 over 2, because we're dividing y squared by y to the 1/2. This would be negative square root of 2g a2 dt. Perfect. All right, now we can go into our integral bounds here. So for time, it's very easy. It's just 0 to t. And then really quickly, if you're somehow still watching this video, take a guess. What are your integral bounds here? If you're guessing it's from 0 to y naught, you're incorrect. And this is where a lot of people get stumped up. We're draining from y naught to 0. So we actually need to go from y naught to 0, which again, it throws a lot of people off. But if you don't do this, you'll end up having an extra negative term in your final answer. which will definitely throw off your final plots. So very important that this is understood. And again, it's all fundamental math. That's literally what a lot of people get stumped up on. So if you're good at calculus and you're very good in your math fundamentals and you don't make any like mistakes like this, yeah, you'll always get the final solution when you apply like conservation of mass. All right, let's evaluate these integrals. So this would just be, again, this is where I'm gonna start rewriting a lot, so bear with me here. Dy, just bringing out our constants from the integral that are not a function of y. And then this integral would just be square root of negative 2g a2 times t. Very simple integral there. And then after you evaluate this integral, I'm going to write this down here and then erase it just so I can kind of stay on the same slide here. But this ends up becoming 2 over 5 y to the 5 over 2 evaluated from y not to 0. This would then be 2 over 5 times 0 to the 5 over 2 is just 0 minus y naught to the 5 over 2. And you're left with 2 over 5 y naught negative to the 5 over 2. So that's what that integral ends up working out to. So I'm just going to erase this really quick. Feel free to pause if you need to understand where that came from. Okay. Just be negative 2 over 5. Y naught to the 5 over 2 times pi tangent squared theta equals negative square root of 2g a to t. Okay, I'm realizing I'm kind of writing at an angle here. It's just it's so hard to write with this tablet, so I'm going to try to write more straight, but um, that's just kind of a state of where we are right now with this writing capability. All right, so we can, take away the negatives, divide the negatives out on both sides. We'll have a positive now. And again, you'll see, if you did from 0 to y naught, then you would have ended up with an extra negative, which would, again, throw off your final answer. So we have an expression for time now. We have this t value. Everything looks nice. Lots of variables here, but now we have to express the result in terms of initial volume and the initial volumetric flow rate. So let's just quickly recap. Let's use blue here. Our initial volumetric flow rate at time t equals 0 would be equal to V2 times A2, which would be equal to the square root of 2g at our initial starting y naught for our cone times A2. And then our initial volume would be equal to this total volume, not a differential, pi over 3 y squared, and technically this will be y naught squared, to be more specific because we're initial volume. And this would be times tangent squared theta times y naught. We're not writing in terms of radius again. Remember, we made that substitution before. So basically, we have to get this kind of gross thing in terms of these two relationships here. So we're just manipulating variables so that we can write them in terms of Q naught and V naught, because Q naught and V naught are buried in this relationship that we found. So let's start off with Q naught because it's pretty easy. I already see on the right-hand side we have a square root of 2g times a2. All we need is a square root of y naught. So we can actually multiply by a square root of y naught on both sides, which you would end up getting 2 over 5 y naught, y naught to the 5 over 2 times 1 over 2. That would be, okay, that would be y naught to the cubed times pi tangent squared theta equals square root of 2g, and we multiplied by a y naught on both sides. So we end up with a y naught over here, a2 times t, and this is our volumetric flow rate. Great, that simplifies down nicely. And finally, we have to get out our initial volume from this, which we're pretty close. We have our y naught cubed. Technically, there's a y naught squared and a y naught here, so this should be y naught cubed. And we have our tan squared theta. We're just missing our 1 over 3. So what we can actually do is just do 2 over 5, and we're going to multiply by 3 over 3, which is just 1, times pi times y naught cubed times tangent squared theta. And from there, this can be 6 over 5 times pi over 3, y naught cubed, tangent squared theta equals q naught times t. This term right here is v naught. So finally, we get our solution for part A, which is 6 over 5 v naught equals q naught times t. And if we're actually just solving for t here, t would be equal to 6 over 5 times v naught over q naught. Very nice relationship there. So we turned this gross thing into something very simple, which is what the question was aiming for. So that's part A. Now, part B is, let's just reassess. If the hole diameter is 5 millimeters, plot the time to drain the funnel as a function of y naught over the range from 0.1 to 1 with 15-degree to 45-degree theta range. So, in our original relationship here, we have y naught and we have theta. So basically, if you were to do this like on a test or an exam or even like a homework, you would just basically plot out. Let's see, it's asking plot the time to drain the funnel as a function of, so it would be the time to drain the funnel, or no, time would be on this axis here, and then maybe you would have like some other variable like theta or y naught, and then you would have kind of how the plots change with time and things like that. So you plot something like that on a test, which in a test you have to hand draw it sometimes. It is what it is, but thankfully we have technology, and I have managed to actually develop a script before here, which kind of saves us a lot of time. So there's some fixed parameters here. You have exit diameter is 5 millimeters. We have our exit area. We have our numpy arrays, which are just theta degrees and y naught as a kind of range here with 200 increments. And from there, it's literally just plotting our final relationship. I determined it be best to plot it in hours, and you'll see why in a second. Because when you plot it, you'll see that the time varies quite a bit, and it can take quite a long time, especially when you have a funnel height of y equals 1 meter, or y naught equals 1 meter, as you can see by this line there. Um, so yeah, that's pretty much it. Like, there's nothing really else to it. Like, there's our kind of final relationship up here. Not sure why that's 6 pi over 15. I guess, because it's multiplying by the 6 over 5 times the pi over 3. It's its final answer there. That makes sense. Um, but yeah, that's it. That's literally all it is for this question. So I say that, but it's been almost 28 minutes of me yapping. So if you have any questions about this, feel free to leave a comment again. If you see anything wrong with the math or have any questions about the math, leave a comment. And with that, I'll stop here on this video, and we'll do one more conservation of mass question after this, and then we'll move on to conservation of momentum. So thanks for watching, everyone. Good luck.